All right, so concavity is what we're talking about today, and we've talked about concavity in pre-calculus. So it has to do with whether your graph is sort of curved up or curved down. But we also talked about increasing, decreasing, positive, negative, all of that stuff in pre-calculus. We weren't doing it from equations. We were looking at graphs whenever we did that. So today we're going to start talking about concavity from the equation, not from, well, we'll look at some graphs too to see how they relate, but not solely from the graph. So if something is concave upward, we generally just talked about it being like curved upward, right? So ways to describe this a little more precisely is something that is concave upward can be decreasing at a decreasing rate. So let's think about what that would look like, okay? So you have, it would have to be going down to be decreasing, right? It definitely would not just be a straight line like that. That would be decreasing at what kind of rate? Constant rates. That would be decreasing at a constant rate because it is just going down over that same rate the whole time. So if you have a straight line, that's a constant rate of change. But before calculus, we talk a lot about slopes of lines. Calculus helps us look at rates of change that are not constant. So if we are decreasing at a decreasing rate, that means at first we'd be dropping really fast. But then out towards the end, we're decreasing still, but at a much slower rate, right? So it drops a lot at first and then slower rate after that. So this is going to be concave upward if you have something that is decreasing at a decreasing rate. You also can have concave upward where it's increasing at an increasing rate. So increasing at an increasing rate is going to be you're increasing slowly at first, just a little bit, and then rapidly towards the end. That causes something that's curved upward as well. So you can be decreasing at a decreasing rate or increasing at an increasing rate. Okay. Concave downward is increasing at a decreasing rate. So something that is increasing at a decreasing rate is going to be going up, and it's going to go up quickly at first and then slowly towards the end. All right, so if it's curved down like this, we would say that's increasing at a decreasing rate. Or our last option here is decreasing at an increasing rate. So if you're decreasing at an increasing rate, you're decreasing slowly at first and then rapidly towards the end. And you can see both of those make something that's sort of curved down looking. Okay, so to talk about concavity, what we're going to have to look at is the second derivative. So if we have something that is concave upward, if a graph is concave upward, the slope of the tangent line increases from left to right. So I'm going to just draw in here an example here for you. Okay, so let's just go with something classic that we know is concave up. If I have just a typical quadratic, it is going to be concave up everywhere, right? The whole thing is concave up. So if you think of drawing in the tangent lines, here we would have a tangent line. Here we would have a tangent line. Here we would have a tangent line. Right here would be our 0 tangent line. Just drawing in a few tangent lines here. And let's think about estimating what the slope of these tangent lines are. We're going to just do an estimate. Right here, that slope of that tangent line would be 0. We could say this tangent line right here has a slope of maybe -1. I'm just guessing, for this. What would you guess for the slope of this tangent line? -3, maybe? And then if this is -3, what would you guys guess for this tangent line? -5 would be a good guess. Right there. And then if I go to the right, let's say this might be 1.5, just because I've not put it, I should have made it symmetric there. What would you guys say maybe for this one here? 4. And maybe over here, 6.3. Okay. Just guesses, at what those slopes might be. But if I'm going from left to right, I've got -5, -3, -1, 0, 1.54, 6.3. What is happening to the slopes of those tangent lines? What's happening to those numbers? They're increasing, right? So if a graph is concave upward, the slope of the tangent line increases from left to right. So if f prime is increasing, then f is concave up. All right, so if our derivative is increasing, f would be concave up.
Is it always left to right?
Yes, always left to right. Yep, always do it left to right. Okay, something similar is going to be true if we have something that's concave downward. So let's do another just classic parabola, but this time upside down. And so like if we drew in this tangent line right here, it'd be 0. Let's draw in, I'll just do a couple to get the idea here. Let's make it more symmetric this time. So this slope right here might be something like 2. This slope right here might be like 5. If this was symmetric, that'd make this -2. That'd make this -5. So this time when I go from left to right, what's happening to my slopes? They're decreasing, right? So, so if f prime is decreasing, then f is going to be concave down. So, when we're talking about f prime being increasing or f prime being decreasing, we can think about that from our second derivative. And did I put anywhere in here where we're going to need to add that in? Okay. All right, so the chart, I'm going to make us a chart here in a second that'll help us here. So if f double prime is positive, then f would be increasing. And then f would be concave up. If f double prime is negative, f prime is decreasing, and f is concave downward. I really like to do this in a chart rather than written out like that. I need to add that to these notes. But I put this. So I did this morning whenever somebody had asked me a question about like how to tell if if a function was increasing or decreasing from the derivative or vice versa. So what we know right now, what you've already done, is that if my derivative is positive, then f of x is increasing, right? So what we just added to it here is we said that, and I would copy this somewhere on your notes wherever you might have some. I probably don't leave enough room, but I would definitely copy this. All right, so we just said if f prime down here to the bottom of this chart the second derivative. That is the derivative of the first derivative. What could you tell me about the second derivative here? It would have to be positive, right? Because the second derivative is the derivative of the first derivative. So if this is positive, that means f prime has to be increasing, right? And if f prime is increasing, that tells us that we're concave up here. So the same as the converse is going to be true here, concave down is going to mean that the derivative is decreasing, which is going to mean that the second derivative is negative. And then we could kind of mark out these two squares right here. Knowing whether or not the derivative is positive or negative doesn't tell you anything about the second derivative. So, in general, the best way, if you're given an equation, to talk about concavity is to look at that second derivative, because we can tell if a second derivative is going to be positive or negative at different points. Sometimes we'll be looking at a graph, and if we're looking at a graph, we might need to look at whether the derivative is increasing or decreasing. So let's look at our first problem that we have right here. So we are supposed to tell the intervals where f of x equals x to the third minus 9x squared plus 24x minus 12 is concave up and concave down. So if I want to know where concavity changes, I'm not looking for the critical points and the places where I change from increasing or decreasing. That'll give me maximums and minimums. I want to know about concavity, which means I'm going to look at second derivative here. So I am going to take my first derivative, which is going to give me 3x squared minus 18x plus 24. And then I'm going to take the second derivative, which will just be 6x minus 18. So, I'm pretty sure that they told me at some workshop that this is not called a critical point because it's second derivative and only the first derivative points are called critical points. So, we have sometimes named these the, like, really critical points, or the, I think technically they're not called critical points, although it's sort of the same thing as critical points, it's just with the second derivative. So, if I set this equal to 0, then that's going to give me 6x equals 18, which is going to give me x equals 3. This is your really critical point, your second derivative critical point. So if I'm looking at that second derivative, 3 is the point where I might change concavity. If I plug a number less than 3 into my second derivative, because I want to know whether it is positive or negative, something like 0, I would get negative 18, so I'd get a negative right here. And if I plug something bigger than 3 in, like 5, I would get a positive number, so I'm going to get a positive over here. So if we think about what this tells us, right? You don't have to make this chart, but I'm going to. If I have a negative, it tells me that the function above it, right, is going to be decreasing and then increasing here. But it's not asking me about the increasing and decreasing of the first derivative. It's asking me about the original function. And if my derivative is decreasing, then I will be concave down here. And then concave up here. Now, you don't necessarily, I mean, you can definitely include this middle line if you want. But you can go straight from a second derivative to telling me about the concavity of the original function. So, and that's what I suggest whenever you write out your explanation here. So I would say f of x is concave down for negative infinity to 3 because f double prime of x is less than 0 for this interval. And I'm having a hard time remembering whether it's parentheses or brackets on this one as well. I know that it's not going to matter because it's going to be like the increasing, decreasing thing. It should be a bracket there. I'm going to have to go look that back up. You cannot say f prime of x is negative because f prime of x is not necessarily negative on that. So f prime of x is decreasing. Yes, you can say it. Yes, that'll be fine. F double prime is negative is perfectly fine. And then we would also say f of x is increasing. Oh, not increasing. What am I doing? Concave up. For 3 to infinity because f double prime of x is greater than 0 for this interval. So in general, whenever you're doing these problems that have equations, you typically want to look at the second derivative, and if it is positive, your function is concave up. If it is negative, your function is concave down. You can look at the first derivative and talk about it being increasing or decreasing, but it's unnecessary because to know that, you have to look at second derivative, so it would just be an extra point of explanation that doesn't have to be said, right? You definitely cannot do it by only looking at the first derivative. You have to look at that second derivative because you can only tell if f prime is increasing or decreasing by looking at its derivative, which is the second derivative. Okay, there's a definition down here at the bottom of that slide. A point of inflection is a point where the concavity of a graph changes. So this one did not ask for it, but if it had x equals 3 is a point of inflection for that graph. Questions? It's a lot like our increasing, decreasing stuff. For increasing and decreasing, you're going to give an interval. For a point of inflection, you're going to say there's a point of inflection because your second derivative changes signs. There. All right, so let's keep going. Why is it not? What just happened? Okay. All right, so we must determine the concavity of f of x equals 6 times x squared plus 3 to the negative 1. So for this one's going to be a little more difficult because it has a more difficult derivative to deal with. So to do our first derivative, this is going to be a chain rule, right? We've got this stuff right here being raised to that negative 1 power. So it is going to be negative 6 times x squared plus 3 to the negative 2 power. And then we must multiply by the derivative of the inside, which is 2x. So f prime of x is going to equal negative 12x times x squared plus 3 squared. Oh, not squared, to the negative 2. Your final answer is going to be to the negative 3 because we're going to have to take the derivative again. But we haven't done that yet. You're just subtracting 1 from that exponent right now. Yeah, so we haven't taken the second derivative yet, but we will eventually. We will. He's a step ahead. So we will get a negative 3. Now, if I want to take the derivative of this, what am I going to have to use? I got to use a product rule. Or you have the option of sending that back down to the bottom and using a quotient rule. It just depends on what you want to do. I think I'm going to go product for this, maybe. So, because this time, I did not have to do a product rule in the first iteration of my derivatives here, because I only had a 6. There was no x with this here. But I now have an x here, so I've got to do product rule. So to take a second derivative here, I will have negative 12x times, and here I will get negative 2 times x squared plus 3 to the negative 3. There's a chain rule hidden inside of here. You got to multiply that by 2x. And that's just half of it. And then we'll have x squared plus 3 to the negative 2 power times the derivative of negative 12x, which is just going to be negative 12. Now, you don't have to simplify necessarily, but it just makes your life much easier to simplify it first, and then we can look at critical points. So if I'm going to clean it up just a little bit first. So this will be, let's see, we'll have negative 12, negative 2, and 2 is going to give us 48 x squared times x squared plus 3 to the negative 3 minus 12 times x squared plus 3 to the negative 2. We are going to factor out this x squared plus 3 to the negative 3rd. X squared plus 3 to the negative 3rd is going to be factored out. So we will have x squared plus 3 to negative 3. And you'll have 48 x squared here, because that'll just cancel out right there. It'll just be gone. Minus 12 times, what's going to happen here? It's just going to be x squared plus 3. And so if we distribute and simplify a little bit here, we're going to get 48 x squared minus 12x squared minus 36. So I'm going to move that x squared plus 3 to the 3rd power back down to the bottom and make that positive, that exponent positive, and we'll have 36 x squared minus 36. If you want, you can factor out the 36 there. It just however you want to do it. I think I might factor out that 36. That'll give me x squared minus 1. X squared plus 3 to the 3rd. You could even do this right here if you want. X plus 1. X minus 1. X squared plus 3 to the 3rd. Yeah, that's just the second derivative. Now we got test, right? The reason I factored that the furthest is because it might make your chart a little bit easier at the very end. So after doing all of that, we finally have our second derivative, and we've got it in like a usable fashion. We had our second derivative here, and if that's all it asked for, we could have stopped, but we got to simplify it so that it's usable. So once we get our second derivative, what are we looking for now? Where we will have positive or negative. And to find that, we've got to find our critical points that maybe technically aren't called critical points, but we'll just call them that for lack of a better term. You're finding the zeros of the second derivative. Yep, they're not zeros of the function, but of the second derivative. And anywhere that would make it undefined. So you're looking for what would make the numerator or the denominator 0. So like for that, 36 times x plus 1 times x minus 1 equal to 0. That's just going to be x equals negative 1 and x equals positive 1. And then if we look at the denominator, x squared plus 3 cubed equals 0. If we cube root both sides, we'll still just have x squared plus 3 equals 0. So we'll get x squared equals negative 3. And we will square root both sides. But what is the square root of negative 3? It's imaginary. It's not going to give you any critical points from that. And if you look at it, you could even recognize that without setting it equal to 0. Because x squared is positive. And then we're going to add 3 to it. And it's still going to be positive. And then we're going to raise it to the third power, and it's still positive, right? So, so there's no way that this could ever be negative or equal to 0 right here. So if you recognize that, you can kind of just leave off that part right there. So we need to know the second derivative. We're going to put negative 1 and 1 here on our chart. And I am going to make myself a chart. So we got 36, we got x plus 1, we got x minus 1, and we got the x squared plus 3 to the third power. So I like to split this up into a chart. You don't necessarily have to. Now, x squared plus 3 to the third, that's positive all the way across, and 36 is positive all the way across. So you can get away with leaving those off, but we won't. And for a positive one, if I plug in something like negative 2, I'll get a negative. If I plug in a 0, I'll get a positive and a positive. And then here, if I plug in something like negative 2, I'd get a negative. If I plug in 0, I'd still get a negative. Anything bigger than 1 would give me a positive. And so this is our final assessment here. Our second derivative is going to be positive, then negative, then positive again. So if our second derivative is positive, what does it tell us about the original function? Is concave up. And if our second derivative is negative, what does it tell us about f of x? Concave down. And I am not, well, should I? How many more of these I got? But, let me look ahead. Yeah, we're going to skip the writing on that one. But you would say, yes. You can. So for these, you should never have to write more than 2 conclusions. You would just say, like, f of x is concave up for negative infinity to negative 1 and 1 to infinity, because f double prime of x is greater than 0 for these intervals. Yes. And you could do f of x is, you don't have to write this down if you don't want, but I'm going to do it real quick, for negative 1 to 1, because f double prime of x is less than 0 for this interval. So you can always combine if you have more than one, because otherwise it really takes forever. Because as long as your reason is the same, you can combine them together, and it will be for those. All right, so I want you guys to have some time to work. So let me think a little bit here on our best course of action. 3 is going to take a little while. It is not necessarily so much more difficult. It is because you have to do the second derivative of something that already requires the quotient rule. Is why it's going to take a little while. And I want to make sure we get through enough, so I'm going to skip 3 for right now. I may come back to it, but I think we'll probably skip it. Let's go to 4, so we need to do a little trig, we need to do a little natural log sort of stuff there. So, f is defined on 0 to 2 pi. They are telling you this because otherwise you have infinite answers to this. Because trig just repeats itself over and over and over again. So it's going to be concave up, then concave down, then concave up, then concave down. It would go on forever. So, they're restricting us just 0 to 2 pi. And we are looking for f of x equals cosine x minus sine x. We're looking for where it's concave up. So if we're looking at concavity from an equation, what we want to look at, second derivative. So f prime of x, our derivative of cosine is negative sine x. Our derivative of sine is cosine x. So we will get negative sine x minus cosine x. So pretty simple first derivative. We got to take a second derivative here. And derivative of sine is cosine, so that's going to be negative cosine x. And derivative of cosine is negative sine, so we'll get plus sine x. So once we find our second derivative, what are we going to do with it? Find the zeros that will give us those critical points. So negative cosine x plus sine x equals 0. And this is an equation that you can't really solve using algebraic methods necessarily. But if I move that cosine over, what I'm really looking for is where sine x equals positive cosine x, right? If I just add that cosine to both sides. I'm looking for where sine x equals cosine x. And while I can't, divide both sides by sine x or do anything crazy there, what I can do is just think about my unit circle and where does sine x equal cosine x. 0, 0 would be right here. It is not on the circle. Pi over 4. Because right here at pi over 4, we have square root of 2 over 2 and square root of 2 over 2. So x equals pi over 4 is one of our critical points. And also over here at 5 pi over 4. So it's negative square root of 2 over 2 and negative square root of 2 over 2. Is it going to be the other pi over 4s? No, because the signs aren't the same there, right? So just these 2 points on the unit circle. Now, if it didn't restrict us to 0 to 2 pi, we would have to do the plus 2 pi k, it would repeat over and over again here. Usually they restrict it, so you don't have to do that. So now what we have to do is we have to put this on a sine line, and we got pi over 4 and 5 pi over 4, and we are testing that second derivative, so I'm going to label this f double prime of x. And so we need to plug a number from each section into f double prime of x. So I would try, what you can essentially think about this section right here, and I'm going to add on, I'm going to put 0 right here, and I'm going to put 2 pi right here. Those aren't critical numbers, but they're endpoints of our interval that we're looking at. So this section right here, 0 to pi over 4, that's this section on our unit circle, right? It's going to be pretty safe to use 0 here. It is an endpoint, so there could be some weird things that happen at it. Definitely, though, we could use pi over 6 right here, right? And at pi over 6, you got square root of 3 over 2, 1/2. So if we think about plugging in pi over 6, we would have negative cosine of pi over 6 plus sine of pi over 6, which is going to give us negative 1/2 plus square root of 3 over 2. We don't care about what that is, we just care about whether it's positive or negative. Is it positive or negative? It is going to be positive. Square root of 3 over 2 is bigger than negative 1 over 2 because square root of 3 is bigger than 1. Right? Square root of 3 is not quite square root of 4, which would be 2, but it's bigger than square root of 1, which would be 1. So we get a positive here. Then we are looking at our next segment from pi over 4 over to 5 pi over 4. So on the unit circle, we're looking at this part. So you can choose anything here. I would suggest either this point or at 180, either one of those because they're a little easier to deal with. This is 0, 1 for our coordinates right here. So if we just use pi over 2, if I do cosine of pi over 2, I'm sorry, negative cosine of pi over 2 plus sine of pi over 2, I will get negative 0. Is that right? Cosine is your x-coordinate, yeah. Negative 0 plus 1. What do I get there? Positive. I've done this right, haven't I? It feels wrong. It usually switches back and forth. Let's see. Oh, no, I've got it backwards on the first part, don't I? Cosine of pi over 6 is our x-coordinate. I have it backwards. Sorry. Okay, let's fix this. I had my 2 coordinates. This would be square root of 3 over 2. And this would be 1/2. And that would give us a negative. Sorry about that. Got my coordinates mixed up there. All right, everybody with me so far? All right, then the last segment here corresponds to this part of the unit circle. I would suggest this point right here at 3 pi over 2 because we've got 0, negative 1 for that, which is going to be easier to deal with than any of the other points there in that section. So if I do negative cosine of 3 pi over 2 plus sine of 3 pi over 2, I'm going to have negative 0 plus negative 1, and that is going to give me a negative in that section. This one only asks us for concave up. It did not ask for concave down, but you pretty much still have to do the whole thing the same way. You just only have to write one conclusion here. So you would say f of x is concave up on pi over 4 to 5 pi over 4 because f double prime of x is greater than 0 on this interval. So it's a lot like the increasing, decreasing stuff we have already done, but we're looking at second derivative to tell us concavity. So if it asks about concavity, you have to take that derivative twice and then look at the sign of that second derivative. All right. Okay, let's look at this problem. And I want to show you guys a trick that you can do for this problem that makes it a lot easier than it would be otherwise. So, back long ago in pre-calculus, we did properties of logs. You actually do some of it in Math 3 as well. I'm not sure if this one you do in Math 3. You do not get to drop the logs on this one as much as Coach would love to drop the logs. So for this, I'm going to write it this way. Natural log of x squared plus 4 to the 1/2 power. And there was a property of logs that told us we could do something with that 1/2. Does anybody remember what we could do? We can bring it out here to the front. And so if I write this as 1/2 natural log of x squared plus 4, it makes it a lot easier to take the derivative. Because now, before I had like a triple chain rule. I had the natural log, I had the square root, and I had the x squared plus 4. Now, instead of having that square root, I just have a coefficient of 1/2 out front, which makes it much easier to take that derivative. So this is a trick that you would want to do ahead of time to make it easier to take that derivative. So when I take the first derivative of this, the 1/2 just kind of hangs out because it's a coefficient. What do I do to take the derivative of natural log? 1 over. So I'm going to have 1 over the stuff on the inside, x squared plus 4. But then what do I have to do? Multiply it by the derivative of the inside, which would be 2x, which I'm going to put it over a 1. So I got all my fraction stuff lined up here. Now, if you want, you can cancel this 2 with this 2 right here. Or you could wait and do it later. And so I will get x over x squared plus 4. All right, that's my first derivative. Now I need to take second derivative. What am I going to have to use for that second derivative? Quotient. So f double prime of x is going to be x squared plus 4 times the derivative of x, which is just 1, minus x times the derivative of x squared plus 4, which is 2x, all over x squared plus 4. And so if we do this, we will get x squared plus 4 minus 2x squared. Oh, wait. Forgot my square there on the bottom. X squared plus 4 squared. And so I will have 4 minus x squared over x squared plus 4 squared. And it's up to you. You can leave it like it is, or I'm going to do 2 minus x, 2 plus x for that numerator. As long as you remember your plus or minus, whenever you take the square root, you'll be fine. I like it this way because I like to make the chart, but if you don't care so much about what your chart, I like the chart to be like as simple as possible and not have squares in it if possible. So I usually write it out like this. But as like right here, if you don't factor it, you're going to have 4 minus x squared equals 0. So 4 equals x squared, and you'll square root both sides. As long as you remember plus or minus with that 2, you'll get that right. There, so this is sort of optional here. So, for this, definitely x equals 2 is a critical point. X equals -2 is a critical point. Do we get any critical points from the bottom? No, because x squared is positive. You're adding 4 to it, which makes it more positive, and then you square it. It's definitely going to be positive, right? It's not going to ever be negative. So I don't even have to set that equal to 0 and try to solve. I'll get a negative under the square root if I do. But if you are unsure about it, you could do that. You got x squared plus 4 squared equals 0. That's x squared plus 4 equals 0. That's x squared equals -4. And then you try to square root a negative, so you dead end on that. So if we do our chart for this, I've got f double prime of x. My pieces are 2 minus x, 2 plus x, and x squared plus 4 squared. We have already said here that x squared plus 4 is going to be positive all the way across there. Really, if you left it out, it wouldn't hurt anything. Be a little careful here, because usually these are like negative, negative, positive. It's going to be opposite here. So like 2 minus -3 is going to be positive, because you'll have 2 minus -3, and it becomes positive right there. If I plug in something like 0, it's still positive. And then if I plug in something bigger than 2, that's where I get the negative. And then here, if I plug in something like -3, here I will get a negative. If I plug in 0, I will get a positive. And if I plug in something bigger than 2, I'll also get a positive. So our final here, our second derivative is negative here, positive here, and negative again here. Now, this one asked us not about concavity, but about points of inflection, right? So it's like the difference between asking increasing or decreasing versus asking for a relative maximum or minimum, right? The only thing that's really different about your work is your conclusion. So since they asked for points of inflection, we are not looking for like giving intervals where we're concave up or concave down. What we're looking for is our concavity switching. So we would say that f of x has points of inflection at x equals -2 and x equals +2 because f double prime of x switches or let's see, from negative to positive or vice versa at these points. I hesitated on that because there's some different ways that you can explain that. You can do them, like with the maximum minimums, we have to do them separately, right? Because a minimum is from when our derivative goes from negative to positive, and a maximum happens when our derivative goes from positive to negative. For points of inflection, it does not matter whether you're going from negative to positive or positive to negative. It just matters that your concavity is changing. Probably the quickest way would be to say that f double prime changes signs at these points, and I wanted, so I almost stopped and rewrote it like that, but I was already too far in. Or you can say that you switch from negative to positive or positive to negative at those points, just explaining that that sign changes. What you cannot do is you cannot say because f changes from concave up to concave down or concave down to concave up, because that is just the definition of a point of inflection, right? It does not show that you have proven it from the derivatives there. So you have to answer it according to what happens to that second derivative. So you're talking about that second derivative changing signs. Okay, questions? Okay. All right, I've got one more I want us to do. All right, it asks us where f of x equals e to the negative 2 over x is concave down. So I would suggest, I'm going to write it like this just because it's, what we're dealing with is negative 2 over x. But I would suggest doing this, e to the negative 2 x to the negative 1. Because if you have negative exponents instead of fractions, it is going to make it easier to take that derivative. So if we were taking the derivative of this one, who can tell me what that first derivative is going to be? Okay? More goes with it. 2x to the negative 2. All right, so the derivative of an exponential is itself. You just copy it down, but then you must take the derivative of the exponent there, which is going to be positive 2x to the negative 2. Before I would move on, I would probably clean this up a little bit and make it 2e to the negative 2x to the negative 1 over x squared. Really, it just depends whether you want to do product rule or quotient rule. You could leave it with negative exponents there. Maybe I just want negative exponents. What do you guys think? Quotient rule. We can do a quotient rule like this, or I could have written it like this, just 2x to the negative 2 e to the negative 2x to the negative 1. And do product rule. Let's take a vote. How many of you like quotient rule better? How many of you would rather do product rule over here? Okay, product rule. Both will give you the same answer.
Yeah, product will give you the product.
Yeah. So, if I take the second derivative, got to use product rule here. So I've got 2x to the negative 2 times the derivative of e to the negative 2x to the negative 1. That is just what we just did, right? We just took the derivative of that. So it is, you could just copy this down again, 2x to the negative 2 e to the negative 2x to the negative 1. Right? This is the derivative of e to the negative 2x to the negative 1. Plus e to the negative 2x to the negative 1 times the derivative of 2x to the negative 2. So that's going to be negative 4x to the negative 3. Okay, questions? All right, let's try to clean this up a little bit, and then we're going to see if we can put it all together. So we'll have 4x to the negative 4 e to the negative 2x to the negative 1 minus 4x to the negative 3 e to the negative 2x to the negative 1. All right, what do you guys see here that can help to simplify this? Yeah, definitely we've got this e to the negative 2x to the negative 1. We can take that out. So e to the negative 2x to the negative 1. Now leave us 4x to the negative 4 minus 4x x to negative 3. Alright, what are your other ideas? I don't like all those negative exponents in it. It's me. Okay, we could move it to the bottom. The negative exponents to the bottom. So I would have 4 over x to the 4th minus 4 over x to the 3rd. And I really need to get common denominators there, right? So I would have an x. I need to add to top and bottom on that second one. So that would give me e to the negative 2x to the negative 1. And I'd have 4 minus 4x over x to the 4th. Yeah. And it's really up to you what you want to do with this e right here, but it's not really going to make a difference because e to any power is always positive. All right? Even though this is the jumbled mess of stuff right here, e to any power is always positive. So it really does not matter. It's not going to give you any critical points, and it's not going to change your sign at all. You can basically just leave it off if you want at this point. What you really need is this part over here. The numerator, 4 minus 4x, if it equals 0, then you got 4 equals 4x, which is going to give you 1 equals x. So 1 is one of your critical points. And then you also can have the denominator equal to 0, so x to the 4th equal to 0, which is going to give you 0 for that. So if we go to our chart, I'm going to put e to the negative 2x to the negative 1 on here, but it really does not affect my outcome very much. I'm also going to put x to the 4th on there, but it is not going to affect my outcome much. 0 here and 1 here. E to a power is positive all the way across. X to the 4th is positive all the way across. So really the 4 minus 4x is the only thing that changes your sign here. If you plug in a negative number, like a negative 1, you will get a positive right there, because you'll have negative times negative, which will give you positive there. Between 0 and 1, you will still get a positive, but anything bigger than 1 is when you're going to start to get a negative. So you will have a positive here, and negative. And what did this one ask us for? Concave down. So your conclusion would be f of x is concave down for 1 to infinity, because f double prime of x is less than 0 on the sample. These are tougher because you got to find second derivatives. So it's generally the same thing we've been doing, but you got to do the derivative twice, which is not much harder at all on those first problems like we did, where it's a simple problem anyway. But on the more complicated ones, it takes you a little longer. So let's see if that's what I got on Canvas. I don't know if that's the same. It is textbook, yeah. I'm looking at Canvas to see if I've got the same numbers there. 3, 10, 13, 19, 20. Let's see. I think I did take a couple off. Let's see. 3, 10. Okay, I took a couple out on the Canvas assignment. So 3, 10, 13, 19, 28, 31. So you got 6 of them there. 3, 10, 13, 19, 28, 31. So you got about 10 minutes. Try to do at least one before you go. Let me double check those and make sure there's nothing crazy there I didn't mean to assign. So it's 242. Here, I'll make that big again now that I've got the numbers right.